Hey guys, so we're going to go over the rest of 10.6 parametric equations. So what we left off on last time was an idea of eliminating the parameter using trig identities, which you don't necessarily have to do, but it does make the problem a lot easier. You don't need to use inverse trig if you just know your identities. Specifically, the identities that we're going to need to know are cosine squared plus sine squared is equal to 1. So that's what we came up with last time. We graphed this. The very tail end of class, we talked about how can I graph this on the calculator. You need to go into rectangular mode and type in the following. That T is the same thing as the X button. And you're actually going to get a circle, which is pretty cool because we do know that x squared plus y squared is equal to some r squared is a circle, which is cool. That means that the parametric equation x equals 3 cosine of theta and y is equal to 4 sine of theta between 0 and 2 pi. We know that this is actually a circle in parametric mode, which is really, really cool, actually. You can actually make some very cool shapes with this. One other thing that I wanted to talk about here was the restriction. Notice here it says the restriction is that theta is between 0 and 2 pi. I mean, this makes sense given the function here. If theta is between 0 and 2 pi, that basically means that we're going to go all the way around the circle, which I suppose, once again, that hopefully makes sense to you. If not, send me an email and I'll talk about it further. All right, so let's go ahead and try another problem. So I'm going to have you guys pause the video, see if you guys can figure out what the parametric equation would be in rectangular form of this example. Okay, so hopefully you had some time to think about this. Let's go ahead and use a similar method that we did last session. So first thing I'm going to do is I'm going to solve for secant. So I know that x minus 1 divided by 3, that's going to equal secant of theta. Similarly, I know that tangent of theta, that's going to equal y plus 3. Well, I do know some formulas for secant and tangent. And that would be, I think, secant squared theta plus 1 is equal to tangent squared theta. I think that's it. Let me double check. Okay, I think I had that a little bit off. I think it's going to be this. So secant squared theta. In fact, let's just derive it. So if I know sine, cosine, 1. If I go ahead and derive this, I guess if I divide everything by sine over cosine, let's divide by cosine. Divide by cosine, divide by cosine. Then I know that sine over cosine, that's tangent, plus 1 is equal to secant. Okay, that looks a little bit better. Okay, so what I do know here, just based on deriving, I told you guys I don't memorize these, I just like to derive them. I have tangent squared theta plus 1, that's equal to secant squared theta. So one thing we could do is we could rearrange this a little bit and get that tangent squared theta minus secant squared theta. That is equal to negative 1, which I guess if we flip this around one more time, we could say this is the same thing as secant squared theta minus tangent squared theta. That's equal to 1. Well, thankfully for us, we already know what secant of theta is. Secant of theta is x minus 1 over 3. So I'm going to replace it. Instead of saying secant squared theta, I'm going to say x minus 1 over 3 squared. And then instead of saying tangent squared theta, I'm going to say y plus 3 squared. So I'm going to say y plus 3 quantity squared. That's all going to be equal to 1. So notice here how there are no more thetas. There are only x's and y's, which means we did it. This right here is rectangular form. Let's go ahead and sketch this, or we can graph it on our calculators and see what it looks like. Okay, so taking a look at the graph here, and you should have gotten something similar. Notice here how it says that our restriction is that we start at pi over 2 and we end at 3 pi over 2. Well, taking a look here, if you kind of scroll onto your calculator, I know your calculator is not in like pi notation, but notice how I scrolled right here, and we would say right here that theta is equal to pi. Down here, somewhere around here if you scroll, you'll get that theta is equal to pi over 2. And somewhere up here, you're going to get that theta is equal to 3 pi over 2. And of course, those are going to be in decimal approximations. So using the restriction here, we'd say that our parametric graph is only going to be the highlighted black section. So our parametric graph is only the highlighted black section. After that, the rest of the graph is just whenever theta is bigger than 3 pi over 2. Okay, so be careful here. These restrictions on the parametric graphs really do make or break the graph. So we can kind of translate that restriction into rectangular form. So taking a look at rectangular form here, we would probably say that all of our values are kind of restricted. It looks like we have no x values that are greater than 0. No values that are greater than 0. So we can see if we can translate that. Okay, so taking a look, actually, this is going to be very hard to graph on your graphing calculator, so I went ahead and graphed it on Desmos. I'm hoping you guys can see this. I think you can. So notice here how our domain is a little bit restricted here because we really want that shape that we had previously. So the shape that we're looking for is probably something that looks like this. Notice here how all of our x values are basically going to be less than or equal to -2, and that's just based on the graph. So notice how this one also has a restricted domain. So let's go back. We can add our restricted domain just based on what we saw in Desmos. There we go, based on what we saw in Desmos. And we can say that our domain is that x has got to be less than or equal to -2 to get a similar region from our parametric mode. Okay, all right, let's go ahead and move on to our very last section here, finding parametric equations for a graph. So I want to find a set of parametric equations to represent the graph y is equal to 1 minus x cubed using each parameter. Well, the first parameter we have here is that t is equal to x. So this is really easy. All you need to do is replace x with t. So there we go. We can replace x squared with t squared, and that is the parametric equation with the parameter t is equal to x. This one's a little bit more difficult, but really not really. What we can do here is we could solve for x, and we can get that x is equal to, I think I'm going to move this over, negative t plus 1, something like that. Yeah, x is equal to negative t plus 1, and then replace into the y equation. So this is going to be y is equal to 1 minus negative t plus 1 squared. And so this right here would be the parametric, portion. We'd have x is equal to negative t plus 1, y is equal to 1 minus this. So we could plug that into our calculator and graph that parametrically. And we could also graph this one parametrically. Notice how the domain restrictions, they shouldn't be restricted at all because x squared is true everywhere, and so is t squared. All right, very last thing I wanted to show you guys was just something cool I thought you guys might appreciate. Is just some cool graphs that you can do using parametric. So one problem is called a cycloid. A cycloid is basically a curve traced by a point P on a circle as the circle rolls along a straight line. So say we have a circle, and this circle is rolling along the straight line. It's just going to graph a certain point. So we'll say like P starts here, and then after it rolls a little bit more, we could say that our point P could be rolling up to here, and then as it rolls some more, point P gets here, and then as it rolls some more, P goes down here until it rolls again and P starts back at the bottom again. So you can kind of maybe see what's going to happen here for a cycloid graph. A cycloid graph is going to look something like this. So P continues to go up, 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 and then down, 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 and then back up, 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 down, 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 et cetera, et cetera. You can actually represent that parametrically. We won't talk about the proof of how to get that per se today, but this would be the equation. It'd be x is equal to some value a, just some coefficient, of theta, which would be your t, minus sine of theta. And the y portion would be a times parentheses 1 minus cosine of theta. So if you graph both of those in parametric form, you're going to get a pretty cool graph. So the last thing I want to show you guys is how can I graph parametric? How can I better graph it? Maybe not even just using a graphing calculator, but maybe specifically on Desmos, because we are working towards doing a project where we get to graph parametric and eventually what we're going to talk about tomorrow, polar. So I'm going to go on to Desmos, and I want to talk about how can I graph things that are parametric. I'm going to show you. So to graph something that is parametric, let me actually clear the screen here. Let me clear that screen. Clear. Okay. Let's go ahead and try to graph something. I think this one's kind of cool. So let's do one that I think is cool. All right, so what you're going to do is you're going to do parentheses, And you're going to type in sine of 7 pi, and then we're going to say t, because that's the going to be the coefficient for parametric. That's going to be basically your y equals. So we're going to basically say this is the same thing as me saying y equals sine of 7 pi t, comma, we're going to do our x equal, which is going to be cosine of 5 pi t. And I want to restrict it specifically. It looks a little goofy here. I'm going to restrict it between 0 and 2. And you can see here you get a really, really cool looking graph. And this is actually a parametric graph. Now, technically the parametric graph, let me actually graph it on the screen. This is just how Desmos interprets it. Technically the parametric graph would be y is equal to, if you want to do it on your calculator, it's going to be y is equal to sine of 7 pi t. X is going to be cosine of 5 pi t. So technically that's what it would have been in parametric mode. I'm trying to think, can you guys, I have no idea if you guys can see my calculator. Give me 1 second. I'm going to see if I can pause this. Okay, taking a second look at my graphing calculator, we're going to switch these two. So actually, we'll say that according to my graphing calculator, we want to make sure that x, okay, I think we're good. We want to make sure that x is the cosine and y is the sine. So I know it's a little bit flipped here. Technically in your calculator, they're just going to go in reverse order. X always starts first. But if you put this into your calculator, it should work. You might have to do a little bit of finicking specifically because we want to go between 0 and 2 in Desmos right here. This is in radian mode. So if you're in your calculator, you probably want to go, if you're in degree mode, you probably want to make t going to be somewhere between t and maybe like 180-ish. So let me show you how to do that in your calculators while we're at it. So let's go ahead and go back and let's use the mouse. So let's see if I can go back. All right, so going back here, I did want to show you that you can in fact put this into your calculator, and I want to show you what I inputted to do that. So in my calculator, give me 1 sec, I gotta move this down. Sorry, this is very finicky. I wish you guys could see my calculator. All right, so in my calculator, this is what I inputted. So you guys can see that here. This is what I inputted into my calculator. Now, if you put into your calculator right away, you're probably going to get a jumbled mess. So one thing that you probably should do is go into Window, and you're going to see Tmin and Tmax. I changed, and I'm in degree mode here, I changed my Tmin to be 0, and I changed my Tmax to be 180. But in radian mode, you could change your T to be 0 and your Tmax to be 2 if you were in radian mode. So you do need to kind of go into your window and manipulate a little bit. Otherwise, you will get a very jumbled looking mess. Okay, that is it for parametric equations. I wanted just to show you that there are some very cool ones out there that you could potentially use for your project. If you have any questions, feel free to send me an email, send me a remind, and I'd love to help you with parametric equations. They're very, very cool.